Thank you very much for the invitation. It's a real pleasure for me to speak at this conference because I know Evgeny probably for more than 25 years. Yeah, because we met for the first time, we met in 1998, I think, in Bilbao. So in Bilbao, yeah, I was doing my PhD, and Evgeny visited our group, and that visit made a huge impact on my research. I would say.
One correction. I think we first met in Moscow in
In Moscow?
1998 at the Cluj conference.
Maybe. Okay. Yeah, you're right. You're right. Yeah, it's true. It's true. Yeah, but still, yeah, that visit I remember very okay. Moscow, it was very short, yeah, period, but that visit was probably 2 months or something like this. Yeah, and you gave a series of lectures. I remember on Lie methods in group theory, especially in theory of finite P groups, and also you shared with us a lot of nice, very interesting open questions to think. Yeah. Since then, my research moved to other directions, but I still use a lot of ring theory in my research. And this talk will be an example of use of ring theory. So the topic that I want to consider today is the topic of subgroups of free groups. So in this talk, F will be always a free group. For simplicity, we can consider only finitely generated free groups, and by H, I will denote finitely generated subgroup of F. So two main notions of this talk is H is compressed in F if for any subgroup L of F such that H is a subgroup of L, we have the following inequality that the rank of H is at most the rank of L. So by the rank of a subgroup, as usual, I understand the minimal number of generators. So to be compressed means that H is not contained in a subgroup having a smaller rank. And inert, the notion to be inert in F means that for any subgroup, arbitrary subgroup of F, the rank of the intersection of this subgroup with H is at most the rank of L. And it's clear that the property to be inert is stronger, yeah? Because here we only have, we consider subgroups which contains H. So the question that I want to address in this talk is the following question, which appears also in Kurovka notebook, and it asks whether the inverse is holds, whether any compressed group is also inert. So this question was raised by Dix Ventura in 1996, and later I will explain the motivation. I will explain the motivation to introduce this notion. But before, I would like to recall some basic facts about subgroups and the standard combinatorial way to study subgroups of free groups. So the way that classical way to study subgroups, finitely generated subgroups of free groups is through Stalin graph. So the Stalin graph can be defined in the following way. So let's fix as a notation. So our group will be generated by the set X, finite sets, X1, Xn, and as I said before, H is a finitely generated subgroup of F. So in order to construct the Stalin graph, first we consider the Schrey graph with respect to H. So this graph has a special vertex. We will have a special vertex corresponding to the class of H. And then, of course, we have from each edge, we have from each vertex, in each vertex, we have an edge corresponding to ongoing edge corresponding to some to any generators. Yeah, to any generator. So this is graph of this kind. So it looks like something finite, and then there are infinite number. There are hanging trees. It looks like something like this, some graph with hanging trees. So if we eliminate these hanging trees, what we obtain this graph, which is called the Stalin graph for H. So let's see an example, and let's see how an algorithm to construct this Stalin graph. So assume we have a
Хорошо. Вот что я нашла в интернете по запросу example that house. Взгляните.
assume we have only two generators, and consider a group generated by these two elements. So in order to construct its Stalin graph, we start first with this special vertex corresponding to H, and draw the path corresponding to these words. So this is the first word. And this is the second word. No, this was. Yeah, so yeah, this word goes to, this is, yeah, it goes to other direction, yeah, because it is, we have x1, 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 and here also we have x1, x1. Yeah. So now what we have to do, we see that there are different edges coming out from the same vertex and having the same labels. So what we do, we identify these edges, and what we obtain, this is something like this. Yeah, after identifying edges, so we have x1, x1, and now we have x2, no, just, yeah, we have x1, x2, and then we have x1, x1. It's after identifying edges, we have, so this, we identified these two edges, and then the same way we are doing for the second word, and the second word we just will appear here, x2. And this is what we call Stalin graph of H. So it's clear that for each group, we can construct in a unique way such a graph, and also we can come back. So if you want to come back, we just have to calculate P1 of the graph with this special edge, and the labeling will give us a representation of this graph as a subgroup of F. And what we obtain at the end, we obtain correspondence between subgroups of free group on lattice X and core direct graphs. So I mean core, I mean that without hanging trees. So the only three hanging trees that I allow is a tree containing the special vertex, of course connected, such that each edge is labeled by some letter from X, and we have this special vertex. And so this representation allows to understand structures and properties of subgroup. For example, if you want to know the number of generators, so if you have this correspondence, so the number of the generators of H is the earlier characteristic of this graph plus 1. Okay, let's introduce another definition. So we say that an extension of two subgroups of F, H, and L is algebraic if H is not contained in a proper free factor of L. So, and the set of algebraic extension is denoted by AHF. So this is subgroups H, such that subgroups L, such that H is contained in L, E is algebraic, such that L is a subgroup of F, and this extension is algebraic. So it's clear that in order to understand whether a subgroup is compressed, so whether it is not contained in a subgroup of smaller rank, it's enough to look only in subgroups from this set A. And another observation, which is much less evident, so it's a bit more complicated, it says that for any element from HF, so if we have a subgroup L, which says that L is algebraic, so the Stalin graph corresponding to this subgroup is a quotient of the Stalin graph corresponding to H. By quotient, I mean the following. So we have a graph. So quotient means that I identify some points, some vertices, and then identify edges with having the same labels. So this is a quotient. And as a corollary of this, we obtain the following. So there is this algorithm that decides whether given collection of elements of F generate a compressed subgroup. So the algorithm is the following. So I start with this set. So the first step, construct the Stalin graph. So the construction of the Stalin graph, it's the same, goes in the same way as I did in this example. So this is, of course, it's easy to write an algorithm which produce from a collection of words, produce the Stalin graph. Then consider all quotients. So we have all possible quotients. All possible quotients. So these quotients always corresponds to some subgroups. These quotients correspond to some subgroups containing our group, a subgroup L, H. And what is important, all algebraic extensions are here. I don't claim that all these extensions are algebraic, but what is true by this claim that by this claim that all algebraic extensions are here. So now I have to check, just check whether this holds, and this I can check looking, as I said, in comparing the Euler characteristic of the graphs which corresponds to these subgroups. So this is a finite process which finally decides whether a subgroup generated by this element is compressed or not. Of course, this complexity might be quite complicated, but it's a finite algorithm. So this is a standard way to combinatorial standard way to work with subgroups of free group, and this is one such an example. Okay, let's put another question. So this is a question also appears in a Kurovka notebook. And he asked, the question asked, is it true that the intersection of two compressed subgroups is again compressed? Again, we can try to attack this question using this Stalin graph. So how can we do it? So we have two subgroups. We have two subgroups, H1, H2. Okay, we know they are compressed, and we want to understand something about the intersection of these two subgroups. So what we can do, we can consider Stalin's graph. They maps clearly on the graph, Stalin graphs corresponding to F. Okay, what is Stalin graph corresponding to F? It's one vertex and edges corresponding to generators. So we have this diagram, and we can calculate push out to this diagram. So this is push out. So it's called fiber product of graphs. And this fiber product, it's a graph, but it's not connected. It's not connected. But what is interesting is that connected components of this graph, okay, I will call it lambda, connected components of this graph corresponds to intersections of this kind, two groups to intersection of this kind. So theoretically, we can study the intersections of two groups analyzing this push out, this fiber product. For example, from this, we already can prove that a free group has Hobson property. Hobson property means that intersection of two finitely generated groups is finitely generated. Because, of course, a connected component of this graph is finite, so it has a finite Euler characteristic, and so the corresponding intersections will be finitely generated. But this, and also we can, for example, obtain a bound of the rank of intersection. Probably you heard about the famous Hannah-Neumann conjecture, which was proposed by Hannah-Neumann in the 50s, where she asked about a very explicit, very concrete bound on intersection of on the rank of intersection of two subgroups of free group. And this method, unfortunately, this method did not work in the Hannah-Neumann conjecture because the bound that you can obtain is not good enough. And the same happens with this problem. So if we try to attack this problem with this classical combinatorial method, so we will not able to prove, it's not possible. Okay, at least it's difficult to prove in this way. It's Yeah, there is no way to prove that intersection of two compressed subgroups is again compressed. Okay. However, if we substitute this in this problem, we substitute compressed subgroups by inert, this result, this claim become very trivial. Okay, let's see it. So assume now that H1 and H2 are inert in a free group, and take a subgroup, arbitrary subgroup. So we want to understand the rank of this intersection. We want to understand the rank of this intersection. And of course, we can apply that the intersection is associative. And now we can use that our subgroups are inert. Yeah. So here we used that H2 is inert, and here H1. So in this problem, if we substitute compressed by inert, the proof is one line, two. Yeah. And similarly, before I constructed an algorithm which decides whether a subgroup or free group is compressed. Similarly, we can ask whether there exists algorithm which decides on for a given finitely generated subgroup of a free group whether it is inert. And in this case, inert, it's very difficult to apply the property inert and produce this algorithm, because before we had to analyze only subgroups which are quotients, and so basically we need to analyze quotients of Stalin's graph. But here, because we have to consider all subgroups of free groups, there is no similar procedure. So we have these three problems. So the first one, which asks whether these two notions are general. The second problem, which asks whether intersection of two compressed subgroups is again compressed. And we see that this is trivial for inert groups, subgroups. And the third question that asks about the existence of an algorithm to decide whether a given subgroup is inert. And again, I showed that this question was solved for compressed subgroups. So this question somehow, of course, the question B and C would follow if we answer positively problem question A, but also they somehow showed that these two notions are similar, but in some sense they are very different. So different problems have different difficulties for these two families of subgroups. So this was some small overview of problems that I want to consider in this talk. But before to attack these three problems, I want to motivate a bit the notion of inert subgroups. The notion to be compressed it's quite natural, because it's, as I said, it just says that a subgroup is not contained in a subgroup of smaller rank. But the notion of inert also appeared in a natural way in the problem about equalizer. So the equalizer conjecture is the following question. So given two endomorphism of free group F, we can define the following subgroup of free group. So it's that consists the elements of free groups where these two endomorphisms coincide. And the equalizer conjecture suggests that the rank of this subgroup is at least the rank of free group. So there is a long history behind this problem. So I will just mention few main results. So one, the first main result is due to Bistvina Handel and 92. They proved this conjecture when two endomorphisms are automorphisms. Okay, in fact, you can realize that you can reformulate this situation about fixed points of one single automorphism, because here you can take inverse. Yeah. This result was generalized by Imrich and Turner in 89, and they prove the same. They prove the conjecture when one of them is automorphism. And again, this is result about fixed points of one endomorphism, because if phi is endomorphism, you can express these equalities as fixed point of some endomorphism. Okay, I have to notice that here it's 89, but Imrich and Turner used the result of Bistvina Handel. So that result was available at that time, and it's really, they use it in order to prove a stronger result. So Dix and Ventura observed the following in 96. So if you start with a subgroup of F, which is non-abelian, then since I assume it's not abelian, I can also consider an embedding of F in L and consider endomorphism of L by composing the endomorphism phi and xi, and apply now equalizer conjecture to this new endomorphism. So in this case, equalizer of these two new endomorphisms will be clearly equalizer of the previous equalizer intersection with L. And now equalizer conjecture in this case implies that rank of this intersection is at most the rank in this case of L. Yeah, because we are speaking about endomorphisms of L. And this was motivation. So if you see to this property, this is exactly that means that equalizer is inert. So this was exactly motivation for Warren Dix and Enric Ventura introduced this new notion inert subgroups. So they realized that if equalizer conjecture holds, in fact, there is a stronger condition, a stronger statement. It says not only that we have a bound on the rank, it says that this subgroup is inert enough. But this equivalence between this conjecture, so as I showed, they are equivalent. The equivalence only holds if we assume both conjectures in full generality. So they started to try this conjecture 2, in the cases where the conjecture 1 was null. And that was exactly what they did in that paper. So they proved conjecture 2 also in the case of between a handle. So in the case where both endomorphisms are automorphisms, and the result for this result when one of them is automorphism was proved recently by Jaikin and myself in 2022. Yeah. So, and I want to mention this paper is exactly because this is very relevant, because the method, so the method, okay, it should, it's almost 25 years past. The method that we introduced was completely different, and it's very relevant for the method that I will present now. So we introduced a new notion, a notion of L2 independent subgroup, dependent subgroup. This notion can be defined for general group, and I will not do it in this talk. So I will define a similar notion, and for free group, it will be equivalent to this notion of L2 independence. And this notion is a notion which comes from ring theory. So let's turn to ring theory and start with a field K and consider the group algebra KF. Again, F here is a free group. So an important thing that we know about KF is that this ring is a sphere, which means that every submodule of a free KF model is again free. Okay, in this talk, when I say model, I mean always left model. I work with left model. And this means that, so it's a situation similar as in free groups. Any subgroup of free group is free. And because of this, we can define also the notion to be compressed in this situation of KF models. So if I have a free model N, I say that its submodel N is compressed if for any submodel, okay, here is submodel of M such that N is a submodel of L, we have that rank of N is at most the rank of L. And by rank of free model, I mean the number of generators, the minimal number of generators. So this is invariant, the cardinal of the basis, of a basis. So this is very similar notion as we define it for groups, but in the case of rings, this notion has the following reinterpretation, and so it's not difficult to show that. Okay, yeah. So it's have the following interpretation that there exists a mysterious division ring D such that to be compressed in M is equivalent to this group to be trivial. So I will not say nothing about this division ring. So this division ring, I can explain it if you want later, but so there is some division ring, and K group algebra is subring of this division ring. And this condition it's not, you can express it in different way. So we have an exact sequence of modules. And now we tensor this exact sequence. Okay, let's put this as D for simplicity. We tensor this exact sequence with D over KF, and we obtain another exact sequence. So this functor is right exact. So here we have exact. But it's not left exact, and here we have what is here we have the Tor subgroup. And so to be compressed, it's equivalent that this map is injective. So this is injective. Injectivity of this map is compressed. And this compact reformulation make things much easier in this ring theoretical situation. Okay. So now, so this is a ring theoretical notion, and now we will come back to groups and reproduce it in groups. So what we do, we have a free group, and we have a finitely generated subgroup H of free group. So I define by IKF the augmentation ideal. So this is the kernel of this map. And by induced model, I mean the left ideal of KF generated by the augmentation ideal of KH. So maybe as KF model, it's nothing more. It's isomorphic as KF model to induced model. So now we can define this notion of DKF independent in F if the ideal, so this left ideal F is compressed in the augmentation ideal. Okay, so I understand that if you see it for the first time, it looks like very strange definition, but let's play with this definition a bit. So I will prove very trivial result that at least this notion implies to be compressed. Okay, just to make this exercise and to see how this notion works. So we have, assume we have H is DKF independent. And I want to show that H is compressed. So I consider subgroup L, and I want to show that the rank of H is at least the rank of L. So this chain of subgroups gives me the chain of KF modules. And because we have that this is independent, it means that this embedding is compressed. It means that the rank of this module is less than the rank of this of the second model. But now, okay, now what we have? So here it's a rank of modules, but the rank of module, so of course you have this, is as a model is the same like rank of group. So augmentation ideal is generated freely by xi minus 1. And in similar way here, because of this formula, we have here its rank of H is rank. So this algebraic notion gives us also notion about subgroups. So this notion of models implies a notion implies this notion on subgroups. But of course, this is quite trivial. We don't introduce this new concept in order to prove this one. There is more complicated results, and first of this is that when K is Q, this notion that I introduced is exactly what we consider it with Iago, with Antolin in this paper. So this was what we introduced in that paper. Also, in that paper, we proved already that L2 independence implies that H is inert. So I showed you that it implies that H compressed, but there is a bit more sophisticated argument which implies that it's inert. And also there is another property, that another claim that we can prove is that if P is prime and we compare independence with field equal to Fp and field equal to Q, then independence of a finite field implies independence of a Q. And this leads us to the following chain of implications. So we have this is independent. So it implies that this is independent. So it's, as I said, it's the same as L2 independent. Okay, this is implies that inert. Yeah, as I said here. Okay, we know that inert implies compressed. And the conjecture that I want to make, that here we have also. Okay. Bad news that I cannot prove the conjecture in general, but a good news that I can prove it for P equal 2. And if we prove it for P equal 2, this circle, from this circle, we see that as a corollary, we see that these two notions are equivalent. Okay, I think my time is over, so I will not explain the ideas of the proof, and okay. Thank you for your attention.